All right. Hi, everyone. Today we're going to be looking at section 6.2. In section 6.2, we're going to be concerned with calculating the volumes of three-dimensional objects. So if the volume of our solid, for lack of a better term, is regular, we can create, a closed form formula for this. So for example here, if this is our solid, we notice that the area of the shape of the base here is the same shape and dimensions at the top, and any cross section I chop, we're still going to have that same half ellipse shape or whatever, the parabolic shape at any base. If I have like a circular cylinder and I chop, every cross section is going to be the same circle that's the same as the bases. If I take a rectangular solid and I chop, every cross section is going to be the same rectangle that's the top and the bottom of our box. So really what we have is, for any of these figures, our volume is going to be the area of the base times the height. Right? So that's pretty straightforward. That's regular geometry. We don't need calculus to do any of that. But what if the object is irregularly shaped? Like what if we have some kooky looking thing like this? So I noticed that the bases have the same shape, but if I take a cross section later on, let's say this cross section is px, the shape is the same, but the dimension is different. That shape is clearly much bigger than the base. So we can't create a closed form formula the same way that we did before, because the cross-sectional area is different at any slice between the two bases, or that's parallel to the two bases. So what are we going to do then? Well, if I take a thinnish slice and just pretend that slice is a cylinder, or is a regular solid, where the area of the base are the same and every cross section is the same. Now I can probably slice that thin enough so that's about right. I can calculate the volume of that little section. And if I do that for every little section until I get to the bases, that would create a pretty good approximation of our volume, right? So if we just take the sum of our cross-sectional areas for each slice, and then the thickness of that slice I'm going to call delta x. That'll be like the height of our cylinder, or of our solid, our regular solid that we're approximating. Right? So that, and if I do that all the way, slice the whole way through, then yeah, that'll give me a good approximation for this volume. And the thinner I slice this thing, the better my approximation becomes. So if I slice this thing infinitely thin, I take infinitely many slices, so each time I add a slice, it has to get thinner because I'm just slicing from A to B, right? If I slice from A to B and I use 10 slices and then I make it 20, by nature they have to be thinner slices. And that becomes then my integral from A to B of A of x dx, where A of x is a function in terms of x, describing the cross-sectional area. So that's the idea. Okay, so that's right there. That was our approximation. Here's a visual where we've kind of like, okay, I took 1, 2, 3, 4, 5, 6, 7 slices to approximate the volume of that weird shape before. We can see that's not going to be quite right, but if we get thinner and thinner slices and more and more and more, each of those slices is going to be a little bit better of an approximation. And if we take infinitely many of these things, we're going to have there this guy here where we take the cross-sectional area, we call it the disk method, because essentially we're slicing like a disk, So that's the idea. So let's do an example here. So we're going to look at show the volume of a sphere whose radius is r. The formula is 4/3 pi r cubed. Now we know the formula. We're going to derive this formula here with calculus. So I've drawn a picture of our sphere. And I've drawn a picture of the cross-section. As I can see, that cross-sectional area is a circle, which means pi times the radius of the circle, maybe I'll write RC there, squared, as opposed to the radius of the sphere. Maybe we'll call that RS, just so we're not getting too many R's running around in this. It's like a pirate convention. I paused so you could finish laughing. So if I look at my drawing here, this y value here is the radius for that cross-section, right? So if this is x, and that's the radius of our sphere, I can calculate the value for y in terms of x. So initially we'd say this, but we need this to be a function in terms of x. So if I look at here, it seems pretty obvious the Pythagorean theorem is going on. So I can say then y is going to be plus or minus the square root of rs squared minus x squared. And because y is a radius, it's a length, I can drop the minus. So my area for my cross-sectional area then is pi, and then r squared. And the squared can just cancel the square root. So now I'm ready to write my integral. So my integral from a to b of a of x dx is going to be the integral of my a of x is pi times rs squared minus x squared dx. And then I just have to figure out the bounds, my a and b. So if I look at my shape here, I'd start drawing my cross sections down here at negative r, and I'd keep slicing until I get to positive r. And since I'm integrating with respect to x, I know that my cross sections need to be perpendicular to the x-axis, right? So I start at an x and I end at an x. We'll see examples later on where we may be slicing in terms of y's. So that's important. Okay, so I'm going to then distribute my integral. So rs is a constant. So I can distribute like the pi through and then distribute the integration across. So far, so good. Ooh, Mr. Kulik just sees a shortcut. Look at this. Hold on, I apologize. Look at our picture of our sphere up here. Let me clean it up a little bit. Notice that this is an even function because we're symmetric across the y-axis. So let's do that. That'll make life a whole lot nicer. I don't know why that became a subscript. That should be a super. Remember that if I have an even function from negative a to positive a, I can just write that as 2 times the integral from 0 to a, because one side is going to be the same as the other. And now I'm going to kind of distribute through my integrals. So I'm going to have 2 pi rs squared integral from 0 to r dx minus 2 pi integral from 0 to r x squared dx. So I do my antiderivatives. The antiderivative of dx is just x. And the antiderivative of x squared is x cubed over 3. And it's a definite integral. So I'm going to actually think about it this way. I'm going to do that just to make life a little cleaner. So when I plug r in, I'm going to have, and that's rs really, 2 pi rs squared times rs minus 2 pi rs cubed over 3, and then minus 0 plus 0. When I plug 0 in for x's, they just 0 out. Okay. So if I look at this, I have 2 pi rs cubed minus 2 pi rs cubed over 3. So I need to make a common denominator. So that 2 will just become 6 over 3. If I look, everything is a common denominator now, or has a common denominator, and there are like terms, pi rs cubed, pi rs cubed. So 6 pi rs cubes minus 2 pi rs cubes becomes 4 pi rs cubed, which is what we're looking for. Now, I took a long time to kind of walk through that. I wanted to make sure I was being careful and showing a lot of work, so nobody was confused on my integration. That's the big idea for this section, so I'm just going to kind of continue through and do some more examples and some more examples and some more examples. So the next one here says find the volume of the solid obtained by rotating about the x-axis, the region under the curve, y equals square root of x from 0 to 1. So what I've done is I've graphed for us the square root of x, and I've graphed it only from 0 to 1. So it's that like little shape there. And we're talking about the area under the curve, so I've drawn in that area. And then we're going to rotate this about the x-axis. So I drew that little guy to show like which way I'm rotating as opposed to the y-axis or some line. So when I do that, this is going to spin around and it's going to make this dome shape, right? So if I look at my dome shape here, that's my cross-sectional area. That shape is a circle. So this is the radius for my circle. that is the same thing as the height of our function, right? This is the point. If this is x, that's the point x comma square root x, because our graph is y equals square root x. So my radius is just square root x and the squared cancels with the square root. So I just have pi x. Now I have to think about my bounds for my integral. So I'm going to start my slicings at 0, and I'm going to be here slicing perpendicular to the x-axis, and keep slicing until I get to 1. So my integral should be 0 to 1 pi x dx. So I can pull that pi out front as a constant, and the antiderivative of x is just x squared over 2. So if I plug in, then I'm going to have pi times 1 squared over 2 minus 0 squared over 2, which just becomes pi over 2. Let's do another. Again, here becomes really kind of important that we're able to imagine what this shape is going to look like, right? So let's do another. Find the solid of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. So we have, here's the line x equals 0, here's the line y equals 8, and here is the line, or the graph of y equals x cubed. So if I'm bounded between x equals 0, so I can't pass the y-axis, and I can't go past y equals 8. The shaded region in here is what we have. And this time we're rotating it about the y-axis, so it's like spinning around the y-axis. So I have something that's going to look like this, where that's my disk. So again, I noticed that, hey, that cross-sectional area is going to be a circle. The radius for the circle here is going to be this. Which is just x, right? Because we're just like x over. The problem is, though, when we're doing our slicing, going to be slicing this way, right? We're going to be slicing with respect to y. So I don't want a of x. I want a function in terms of y. So I have to rethink this now. So I know that pi x, or x is my radius, right? And I know for this point, x comma y, that's part of this curve. So it's going to be y, or it's going to be x comma x cubed. But what I really want is this thing in terms of y. So if I go back to my original, and I solve this original equation for x, I do the cube root of both sides, and I get that y is the cube root of x. I'm sorry, that x is the cube root of y. Yikes. So I can just plug that in for x. And now we're good to go. So again, because we're slicing horizontally, we're going to go from 0 to 8. And then pi cube root of y squared dy. So again, everything is in terms of y because we're slicing horizontally. We're slicing perpendicular to the y-axis. So I can pull out the pi, and I'm going to simplify cube root of y squared. I know the cube root of y is y to the 1/3. So y to the 1/3 squared, we multiply our exponents. 2 times 1/3 is 2/3. And now I'm ready to do my antiderivative. So I'm going to add 1. That gives me 5/3. So I have 3 pi over 5 times 8 to the 5/3 minus 0 to the 5/3. And 8 to the 5/3 is, can you do it in your head? Let's see. So we have 8 to the 1/3 to the 5th. So 8 to the 1/3 is 2. 2 to the 5th is 32. And 32 times 3 is 96 pi over 5. You could have typed in your calculator too, but like, should be something we can do in our head. We might have to think about it for a moment. 8 to the 1/3 is just 2 because 8 is 2 to the 3rd, and 2 to the 3rd to the 1/3 is 1. Okay. Let's look at another example. Here it says we have the line y equals x and the curve y equals x squared. And I want to take that area between the two curves, calling that this fancy R. And we want to find the volume of the solid when I rotate that about the x-axis. So again, we're getting kind of like a circle here when we do this, right? The dealio, though, is there's going to be like a hole in our circle. Right? It's going to be like that. So when I do my cross section, I'm going to get like a donut. So the area of this cross section is going to be the area of the outer circle minus the area of the inner circle. So the area for the outer is pi r(O) squared, and the area for the inner would be pi r(I) squared. And my cross-sectional area then is going to be AO minus AI, which is going to be pi r(O) squared minus pi r(I) squared. Oops, pi. And if I factor that pi out, it's going to be RO minus RI. And now if I think about this in terms of functions, it's going to be like the area of the outer function minus the area of the inner function. So when we do this, we update, instead of calling it a disk method, we call it a washer, because that looks like a washer, like not a washing machine, but like the hardware, like when you have like a thing and you put the screw in, you know, and then like it keeps the screw head from like smushing the wood underneath it. It's called a washer. So let's find then the volume obtained by this problem in exam, or the same. So it's the same solid, but this time we're going to be rotating about the line y equals 2. Okay, so this is the line we're going to be rotating about. So here we're at like 1, 1. So up here we're going to be like, the distance from here to here is 1 unit. So it would be like there. That's going to be like my circle. And the distance here is like 0 to 2. So that's like 2 units. So the distance here would be like 2 to 4. So that's going to be like 4 units. So it's going to be like my other circle. Now if I look, the inside edge of this shape is going to be a straight line, because it's y equals x, but it's going to be like, the shell's going to be like thicker on the outside than it is on the inside. So it kind of looks like that. That's what I'm imagining for my shape. So if I take my cross section here in the middle, my outer radius is going to be to that curved function, and my inner radius would go to the straight line. So both of these are going to be circles, right? So I'm still making a disk. So let's think about what the distance for the outer radius is going to be. So the outer radius is going to be the value of, let me pick a new color here. So I'm actually going to think about the outer radius going like here. I'm going to think about it going down. So the outer radius, I know here to here is 2. And I know right here is the y coordinate at that point. So my outer radius should be 2 minus that y coordinate. And for that line, that was the line y equals x squared. So that's going to be my outer radius. My inner radius, we're going to think about the same way. So again, I know that this distance is 2. And that distance, again, is the y. Now, this line is the line y equals x. So that y coordinate is just x. I'll write it as. Okay. Now we are going to be ready to do our integral. So we're integrating from 0 to 1, pi, and then my r outer is 2 minus x squared, and I have to square it because it's a circle, minus the r inner, 2 minus x, and again it's squared because it's a circle, and then dx. Couple of options here. You could do a u substitution, but I think it's probably just going to be simpler to FOIL this stuff out. I don't think that's going to be too bad. But if you wanted to do like distribute your integral and then do like a u substitution there, that would probably be okay. I'm just going to FOIL things out. And I distributed the negative when I FOILed that out. And I just did that quickly in my head. If you can't do that, you can always write it out in stages or whatever you need to. But we're just talking about like Algebra 1 FOILing. Oops. Let's sneak that pi in there. So what do we have here? We have x to the 4th minus 5x squared plus 4x dx. So we'll do our antiderivative. Still got that pi out front, so I'm going to have x to the 5th over 5 minus 5 times x cubed over 3 plus 4 times x squared over 2 from 0 to 1. And that's lovely because, well, I know when I plug the 0 in, everything just goes away. So I have like pi over 5 minus 5 pi over 3 plus 2 pi. And if I can certainly combine those into like terms, that's going to be 3 pi over 15 minus 25 pi over 15 plus 30 pi over 15. So that's going to give me 8 pi over 15. Okay. What if we instead take that figure that we had before? Again, remember we're talking about that area. But this time we're going to rotate it around the line x equals -1. Okay, well, let's see. That's 1 unit to there. So the bottom of my circle should be there. And here we're at 1, 2 units. So this should be 1, 2 units over. So my shape is going to be like that. Now the inside is still the straight line, and the outside is still like the bulge. So that's kind of like what my shape looks like. So my inner radius is there, and like my, oops, let's put it down here somewhere. My outer radius would be like there. Everybody okay? So let's look here. I know that this distance is 1. And this distance is just going to be the x-coordinate for that point. Oops, but that's a plus, right? Because it's 1 and then x more. But the problem is I don't want that written in terms of x because we're rotating about the y when I draw my cross sections. My slices are going to be perpendicular to the y-axis. But I know that this was the line y equals x. So I can just replace it there, x with y. And then my r outer, again, that distance is 1. And then that distance is the x for that point. But this curve was y equals x squared, or the square root of y is equal to x. Again, I need it in terms of y. Again, since we're talking about a distance, when I took the square root, I dropped the plus or minus and just took the plus because we're talking about a length. It's a radius for a circle. It can't be negative. And now we're ready to integrate. Again, we're starting at the y-axis at 1. And we're integrating up to positive 1. So the integral from 0 to 1. And then r outer is 1 plus square root y squared, pi, minus r inner 1 plus y squared, and then dy. Again, you could do like a u substitution to do this, or you can just FOIL everything out. I think that's the route I would go because the foiling is not too difficult. And if I combine my like terms, I'm going to have those guys cancel out. I have negative y squared minus y plus 2 square root y dy. So if I do my antiderivatives, I can have negative y cubed over 3 minus y squared over 2 plus 2 times y to the 3 over 2 over 3 over 2. Evaluating from 0 to 1. So when I do that, I'm going to have negative 1 cubed over 3 minus 1 squared over 2 plus 4/3 1 to the 3/2. And then we have plus 0, minus 0. Again, all of them have a y in it, so when I plug the 0 in, they just all zero out. When I say them, I mean like the terms of my antiderivative all have y's in it. So when I plug 0 in for y, I just get big old fat 0. So I have pi times negative 1/3, negative 1/2, and then 4/3. If I make myself a common denominator, that would be negative 2 pi over 6, and then plus negative 3 pi over 6, then plus 8 pi over 6. So I end up with, I wrote an 8 down there. So I end up with 3 pi over 6 or pi over 2. Let's try this one. So figure 12 shows a solid with a circular base. So let's draw that with radius 1. So like x, y. And since it's radius 1 and I've chosen to center it at this origin, we know that equation is x squared plus y squared equals r squared. It says parallel cross sections perpendicular to the base are equilateral triangles. Find the volume of the solid. So if I take like one of these, that's going to be like my equilateral triangle. So if I call this like A, B, and C, it's like A and, oh, shoot. Nope. Look, it's on, A and B are on opposite sides of the x-axis. So that's like A and B. So this is, A is like the point x comma y, and B would be the point like x comma negative y. So this is like y, that's like y. So my length for AB should be 2y. FYI, sorry. Since we're the parallel cross sections are equilateral triangles, my area function I'm trying to write is 1/2 base times height, right? So base is going to be that length AB, but the height is going to be this distance here. We'll figure that out in a second. So AB is 2y, but I'm going to do this in terms of x. So I need to rewrite y in terms of x. So if I take this, y squared equals 1 minus x squared, or y is equal to the square root of 1 minus x squared. Again, I drop the plus or minus because I know we're talking about a distance. So it can't be negative. So there's my AB. And if I think about that equilateral triangle I just drawn, A, B, C, we know it's equilateral, so everything is a 60-degree angle. This side was y, that side is y. So this is like a 30, 60, 90 triangle. Short side is 30. The hypotenuse is 2 times the short side. And then the middle side is root 3 times the short side. So the height then is going to be y times the square root of 3. And our y was 1 minus, or square root of, 1 minus x squared. So my area function is 1/2 my base times my height So that's going to give me, when I simplify that down, just square root 3 of 1 minus x squared. Again, the 2 times 1/2 cancel out. And when I multiply these two together, the radicals cancel. So we're going to be integrating now from -1 to Yeah, -1 to 1 along the x-axis. And this is symmetric. So really we're going to think about this as 2 times 0 to 1. So we're going to have 2 root 3 integral 0 to 1, 1 minus x squared dx. It's going to be 2 root 3 x minus x cubed over 3 from 0 to 1. So I'm going to have 2 root 3, 1 minus 1 cubed over 3. So that's 2/3, and times that is going to be 4 root 3 over 3. Okay. Find the volume of a pyramid whose base is a square with side length L and whose height is h. So I'm going to try to draw this. I'm going to embed this onto the xy axis. And I like integrating with respect to x, so I'm going to choose to kind of draw my pyramid this way. Okay, so I know that here's 0, and this would be h. So we're going to be integrating from 0 to h. And my area function is a square. So side length squared. If I take any old thingamajig here, that's going to be like 1/2 L, right? But like, let's take a look at what we got here. So if I look at this triangle here, maybe we'll call this whole side L. And I look at, let's use green, this triangle here, and that side is cap L. What do I have here? Similar triangles. So this height is x, and that height is h. So we can say that like x over L, let's use a different color. So if I solve this, I can say little l is cap L over h times x. And these are constants. Those were given to me, so that looks good. So we're going to have L over h times x squared dx. So I'll square that thing, and L and h are constants, so those can just get pulled out. So we're just integrating x squared dx. So we're going to have L squared, over h squared times h cubed over 3, and then I guess minus 0.
So that's going to come out to L squared H over 3, which makes 1/3 area of the base times the height, which is definitely what we know the area for a pyramid to be. All right. Whew, that was a workout. We're going to do this section twice. So first time through, if you guys can look at 1 through 17 odd and 31 to 33 odds, that would be great. And we'll take questions for sure next time. I'm sure there'll be a bunch. And talk about another way to do this kind of a problem if something else weird happens. Because there's another approach to doing this. Anyways, but that's enough for today. Was enough for today probably half an hour ago, but I'm sorry. Have a good day. Bye.